virtualization basically is a process to create multiple virtual machines on top of a shared set of physical infrastructure. So on the left side is a traditional architecture.
Use the microphone.
So, okay, I'll use the mic for the introduction. Hello. So fortunately we got all the projectors up and going, and so we're going to have Deng Pan presenting on traffic-aware placement of interdependent NFV Middleboxes in SDN networks. A little bit about his background, that he received his undergrad and master's degrees in computer science in China from Jiaotong University, and then PhD in computer science from State University of New York at Stony Brook in 2007. I was just at Stony Brook recently. I think they have a new computer science department. I was there for a conference. I guess it probably wasn't there when you were there. He's currently associate professor in the School of Computing Information Sciences at FIU, and his work mostly is, you'll hear a lot about it today, a lot of different topics related to networking. So are we good with the...
No? Use the computer? Maybe just call computer, yeah. Or bring it back. Is it back? Whoops. So can you ask? Oh, yeah, it's back. It's back.
Okay.
Fine. Okay. All right. So good afternoon, everyone. Welcome to the talk. So this talk is based on our recent Infocom paper that was presented this May in Atlanta. So joined with some of my students and Dr. Liki Pisilo. So I would like to share with everyone some of our recent research progresses on network function virtualization. I hope my talk will be helpful to everyone, either to let you learn more about the current research in the networking area, or it will inspire you to find similar problems in your area. So I'm going to start with some of the keywords in the title, that is virtualization. So as a computer science major, right, each of us knows what virtualization is. Virtualization basically is a process to create multiple virtual machines on top of a shared set of physical infrastructure. So on the left side, it's a traditional architecture. About 20 or 30 years ago, as you can see, you have this hardware box, and the operating system is running directly on the hardware. So on the right side, as you can see, it's the virtualized architecture. So between the operating system and the hardware box, there is an additional layer called virtualization hypervisor, so that it will allow multiple operating systems to coexist on the same hardware box. Because of virtualization, there will be many benefits. Right? For example, reduce the cost. If you have a mail server, if you have a FTP server, right, now you can combine them on a single box, right, reduce the hardware and operation cost. Also, it has a nice feature of elastic scalability, which means that if you have a startup company, right, initially you can just buy a single virtual machine from AWS or Microsoft Cloud Computing platform, and with the growth of your business, you can buy just more virtual machines. And it also has a nice property of fault tolerance. Right? If you need to maintain the hardware, you can naively migrate the virtual machine from one hardware box to the other hardware box without service interruption. Okay, so there are a lot of vendors for virtualization solutions, right? Among them, Deng, right, is a solution provided by Citrix, right, which is located in Fort Lauderdale, near Miami. So network function virtualization is the application of the virtualization technology to the network domain. Okay, so NFV converts traditional network appliances, also called Middleboxes, to virtual machines running on standard servers. So again, on the left side, you can see this is a traditional configuration, right? In order for the network administrator to manage the network. there will be a lot of such hardware appliances, like the firewall, like the intrusion detector, right? Like the proxies, all those kind of. Each of them is a standalone hardware box. So the NFV solution will just run all those network functions as virtual machines. So you can buy those standard, very powerful NFV servers, okay? And then all those different network functions will be running as virtual machines. So we have, because of this NFV new technology, we have the opportunity to optimize the service location for our traffic. So this is an example. If you have such a network, right, of 4 loads, so in a traditional case, you select one of them, right, you put your firewall, and that's it. Right? Usually you don't move it after that. However, for the NFV configuration, each switch will have some of those attached NFV servers. And you can select which server to run your firewall. Right? So in order for everyone to understand the context, I'm going to use an analogy to help you take a look at this problem. Let's say you are running a restaurant, right? And then if it's a traditional the restaurant business, you just find a location for your restaurant, right? So in this case, I may select the downtown because that's where the most population is, right? So once you have selected that location, all you need to care about is how to attract the customers to your location, okay? On the other hand, if you have a food truck, right, like the one near our library, okay, so you have the opportunity to select the service locations, right? Maybe during the weekdays, you will drive your food truck to Coral Gable because there are a lot of companies, right? So those employees will buy lunch boxes, burgers from your food truck. And during the weekends, maybe you drive your food truck to South Beach, right? There are a lot of visitors, so they may buy food from the food truck. So just like the food truck gives you the ability to optimize your restaurant service based on the input, right? Here the input is a day of the week. So NFV technology also gives the network administrator the ability to optimize the service based on the input, right? Here the input is the traffic flows. So of course, running a computer network is much more complicated than selling burgers, right? So we got to take care of more challenges in order for NFV network to run smoothly. Right? So one of them is the Middlebox traffic changing effects. So Middleboxes may change the traffic value of process flows and may do it in different ways. Right? I'm going to give several examples to show what it means. Right? So the first example is the Citrix Cloud Bridge Wine Accelerator. Right? So everyone knows that we have some file servers in our department. Right? In addition to that, we have a backup server in Tallahassee. Right? So if this server is taken down by the hurricane, we still have backup access through the Tallahassee server. So we need to back up a lot of data, right, daily from our location to the Tallahassee location. In order to minimize the amount of traffic, right, we would like to compress the traffic before we send it to Tallahassee. So this is one of the network function provided by the Citrix Cloud Bridge Wine Accelerator. It will compress the traffic up to 20% of its original value. Okay, so the next example is the BCH encoder. Right, it was used in satellite communications. Right, we know that for satellite communication, this is a long distance. There will be many interferences and many transmission errors. So how do we ensure the reliability of the data? Or how do we make sure that all the data transmitted are correct? So we add the checksum. Right? So in addition to the data bits, right, you need to add the checksum bits. Right? So that will increase the traffic volume, in this case, to 130% of the original value. And finally, firewall is a special case. Right? Firewall, there are two possible consequences. Either allow the traffic or stop the traffic. Right? In the previous case, it's 100%. Right? Just one. In the second scenario, it's 0. Okay? So I'm going to use some examples, numeric concrete examples to motivate this research. So let's assume that we have two Middleboxes. Right? So we are going to implement them as virtual machines. The first one is a tunneling proxy that will add 5% of overhead. And the second one is a one accelerator will compress traffic to 50%. Okay. Let's assume that each server, right? Each server can host only one virtual machine, right? Just for the purpose of this example. So let's look at the first scenario. In A, we host M1 right, on V1 and M2 on V3. So let's assume the initial traffic is 1 unit, right? Is 1. So after it was processed by M1, the traffic amount will be 1.05, right? And then 0.5. And after it was processed by the second Middlebox, it will decrease to 0.53. Okay. So how about if we switch the locations of those two virtual machines? We put M2 on V1 and put M1 on V3. Right. In this case, initial traffic rate is still 1, but after it was processed by the M2, the traffic rate will be 0.5. And what is right? So after it was processed by M1, it will go back to 0.53. So comparing the scenarios in A and B, we can see that the locations of those NFV Middleboxes do matter, right? Because in scenario B, we reduced the link load from 1.05 to 0.5. Okay? But that's not the only constraint faced by NFV Middleboxes. So there is another constraint is the dependency relation that may or may not exist between Middleboxes. Right? So here I also have two examples. For example, IPsec proxy is usually placed before NAT gateway. Right? NAT gateway means a network address translation. Is a translation from the public address to the private address. Before we do that, we would like to terminate IPsec tunnel. Right? So we know what the real IP address is. However, in the second example, the virus scanner, it doesn't matter, right, where you put it, because it scans only the payload, not the header. So you can put it either before or after the NAT gateway. Okay. So let's get back to the previous example. Now let's assume that if we add this constraint, that M2 must be placed after M1. Okay. With that constraint, the configuration in B is now invalid, right? Because we put M1 on V3, that is after M2 on V1. However, we can still move M2 from V3 to V2, right? So if you compare the scenario in A and C, we reduce the traffic link, right, of this link of V2, V3 from 1.05 to 0.53. Okay. So this is let's see the overview of this research. We study the optimal placement of NFV Middleboxes, and in particular, we consider different traffic changing effects, right, of the different network functions, and also the different dependency relations that may or may not exist between those Middleboxes. Our objective is to achieve load balancing so that there is no congestion, right, and the end-to-end delay can be minimized. Okay. So here I would like to use two slides to explain the design philosophy of our solution. So we know that in the network, there are two broad categories of flows. So one of them is the elephant flows. They are large and persistent. Although the number of elephant flows is only 10% of all the flows, but they constitute for 90% of all the traffic. So the other category of flows is mice flows. Right? They are small and they are transient. There are a lot of them. About 9% of all the flows are mice flows, but they account for only 10% of the traffic. So our design philosophy is that we are going to allocate exclusive Middleboxes for each elephant flow, which means that we don't want elephant flows to compete for resources. So for every big flow, we allocate those dedicated virtual machines for them. And if they have remaining processing capacity, we're going to utilize those remaining capacity by those mice flows. So in this work, we'll only focus on the elephant flow part, right? So our ongoing work is about if you have some Middleboxes have been placed, how do you utilize leftover capacity, right? By scheduling those mice flows, right? We already submitted that work to a conference, and is currently under review. Okay. So in this work, we also have a testbed implementation, right, using the software-defined networking technology, right, which is a really hot area nowadays. If you read most of the networking papers, right, more or less, they are related with software-defined networking. And the concept is very simple. So if you look at this is a traditional network, the data plane and the control plane are distributed, right? So each switch or router will make their own decisions. How do I forward my traffic? So for SDN, the only difference is that SDN introduces a central controller. So this central controller saves all the traffic in the network, right? So it's like you have a brain that knows everything about the network. So you, of course, you can make a better decision, right? Because it's globally optimal. Okay. So our contributions in this work, I summarize them as follows. First, we formulated this traffic-aware placement of interdependent Middleboxes problem as a graph optimization problem. And then we design optimal algorithms for special cases. And then efficient heuristics for general cases after we prove that the general case is NP-hard, right, with low polynomial time optimal solutions. And then we also implement the proposed design in a SDN-based prototype and validate its effectiveness with extensive simulation and experimental results. Yes?
Can you clarify a little bit? So is a Middlebox the physical box, or is that function that is being...
Just a function, just network function. So it could be implemented as a hardware appliances, or you can also be implemented as a virtual machine. So you can...
Like you cannot really optimize the placement of physical boxes, because that would be dependent on some physical topology of the network or rack or...
Yes, that's why my title is optimization of the NFV Middleboxes. Right. So.
So Middlebox in this term is virtual.
Just functions. Just you can use network functions to substitute anywhere Middleboxes appear. Okay. All right. All right. So I'm gonna briefly explain some of the related works. Right, so there are several categories of related works. The first one is NFV hardware and software architectures. Right, many of the recent research efforts have been dedicated to designing efficient NFV hardware and software architectures. Right, so our work can benefit from those research advances by utilizing those platforms as a foundation for our implementation. So the next category of RelateWorks is a network service chaining. It has been recognized as a challenge to implement a chain of network functions, right? As I showed just now, some of the network functions, they may have dependency relations, right? You have to put this after a certain function. So it is a challenge to do that. So our difference with the above works is that in addition to modeling the problem, we also propose practical algorithms and conduct evaluations based on prototype implementations as well as large-scale simulations. Right, so it's not just a theoretical model. We also have practical algorithms with low time complexity and a real implementation. Okay, so this final category of related work is SDN-based Middlebox deployment. Right, so due to its capability of global optimization, SDN is commonly adopted as a control architecture to maneuver NFV traffic. Right, so if you read the recent papers, SDN and NFV often come together. Right, usually if you want to optimize your NFV traffic, it's better to use SDN because it gives more control, gives you more control. So our work differs from the above ones by not only implement the correct policies through SDN, but we also consider some other challenges or constraints. That is the traffic changing effects and dependency relations between Middleboxes. Okay, any questions? All right. Okay, so if no, I'm going to present the problem formulation. All right, so on this slide, I don't want to use those mathematical formulas. So just in plain words, right, what the study the problem is. So given a network with switches, right, links, NFV servers, and you also load the existing traffic. What does existing traffic look like? And then here comes a new elephant flow, right? Here comes a huge flow of long duration. So you load the source, destination, traffic rate, and the set of Middleboxes it requires. Okay. So our goal is to find a path in the flow, right? You want to find a path from the source to the destination. So in addition to that, we also need to determine the locations of the path, on the path to place Middlebox virtual machines, okay? So as to achieve optimal node balancing, right? So in addition to the routing problem, we also look at the service location problem. Where do you want to implement the virtual machine for a particular network function? Okay, and in order to achieve the best node balancing. Yes?
So just want to make sure that you are in the SDN, there are one controller.
Yes.
I'm considering this central controller.
Yes.
Even though they are like distributed controller is also available for
Yes.
SDN. But for your case, like any of the Middleboxes, and you're considering them as VMs, where will they run?
So
Or will they deploy in which portion, which servers? These controllers or somewhere else?
no, it's everywhere. So like this is the example, right? You have some switches in your network.
But
For-
those are physical switches, right?
Yeah, physical switches.
Okay.
Yeah, and then for each switch, they may have some servers. So you bought those powerful NFV servers and you put them not everywhere, but selected locations in your network. So you have those multiple locations that you can run your virtual machine. So you have to select one of them to implement the virtual machine.
Yeah, that's for like when you're making a physical network with, or when you want to equip the physical network with NFV capability.
Yes.
Right. But then you are talking in the context of SDN.
Yeah.
So then the SDN is different from any physical network because it has like the forwarding switches and the controller is, everything happens in the controller, like all the decisions.
So in our problem, we just assume that the central controller knows the traffic load of each link. So it knows the congestion level at different places of the network. So that will be used as some input for the later algorithms.
Okay. So you have these NFV servers plus the controller as well.
Yes.
Okay.
So the controller is just control how the traffic goes.
Yes. Yes.
Yeah. All right. Yes. Sure.
So just, I want to be sure I understand about elephant flows.
Okay.
So I think the point of elephant flows is that it's a very predictable rate. So instead of having a flow that could go up and down dynamically a lot, you're assuming that the elephant flow is very steady, so you can just measure the flow rate as just a single number that's not changing over time. Is that correct?
Yes, that's one aspect. So also it is the rate is really large, and it has a long duration.
Right.
So for those nice flows, come and go. So maybe before the calculated optimization scheme becomes effective,
Right.
they already
Sure.
it's already gone. Yeah.
So,
And
sort of static flows in a sense.
static flow, exactly. Okay.
Right.
Okay. So here some of the detail of the problem formulation. So each of them is a load, right? Is a load in the network, and then we do some abstraction. SC is space capacity. V is the number of Middleboxes or number of virtual machines that can be hosted by this node, right? Well, we did some abstraction here. For example, this switch, right, has 2 servers. Maybe each server can host, let's say, 10 virtual machines. So in total, the space capacity of this load is 20, right? Because it can host 20 virtual machines altogether. Okay, and UV is a link. Okay, and each, just like any networking problem, right? Each link has a cost. What is the weight, right? If you want to select this link in your path, what is the cost you have to pay? Yes.
This may be a silly question because this is not my area, but why could a flow have its own middle boxes? What's an example of
Oh, it's an example.
Yeah.
So let me give you an example. Let's say you have a web camera, right? Capture some of the raw video, and so there are several things you want to do. First, you want to encode it, use H.265, and then you want to add the videos of different resolutions. So it's like a bunch of functions you need to apply to this data stream.
And you're saying that would happen at this NFV level, not on the computer to which the webcam is attached? I guess.
Yes, you could do that, but you can also think of, this is just an example. Let me give another example. So let's say you are connecting from your home using VPN, right? So you have an IPsec tunnel. So before you send any traffic back to the school, you have to first terminate the VPN tunnel, and then there is a intrusion detector. You need to scan your traffic. So there are 2 functions: VPN terminator and traffic inspector. So they need to apply to your traffic stream. This is just a general example. There are many other examples. So in general, you need a number of functions to be applied to this data stream. Okay? All right. So each link has a cost, and the cost of the path, right? So for example, in here, we have a cost of 2 links, and the cost of the path is the sum of the cost of the both links. Okay, and our optimization goal is just to minimize the path cost, right? Just like Cisco EIGRP or OSPF, right? All those existing network routing protocols to minimize the cost. Okay, so here is how we model the Middleboxes. Right, so M is a set of required Middleboxes, or you can say it's a set of required network functions. And each of them is big M is a set, small m is one of the functions, and they have some properties. One is a ratio, right? How much will this network function change the traffic value, right? Some numbers we saw earlier, 30%, right, or 25% of the original value. The second property is the dependency relation, right? We use M, right, left arrow M prime to represent M must be placed before M prime, and this dependency relation is a strict partial order that is irreflexive, transitive, and asymmetric. Okay. So here are the decision variables, right? What we want to calculate. So it's just two variables. The first is route, right? How do you want to route this data stream, this flow? The second one is place, right? Where do you want to implement each of the requested network functions? Okay, so that's problem formulation. I didn't get into the detail, right? Just give you an overview. So next, I'm going to present the algorithm design, right? How did we solve the problem? So we solved the problem in two steps. In the first step, we assume that the network path is already determined, right? So we only need to care about the service location issue. For example, in this tree network, right? In a tree network, we know that there is only one path from between any pair of nodes, right? So in this case, the path is determined. And however, right, on this path, right, so each switch may have attached NFV servers. So you still need to determine where to implement the virtual machines, right, for the desired network functions. Okay. So we just need to determine where to put each Middlebox, right, virtual machine. So only to calculate the place, right, route is determined.
And does this decision change with every new flow coming?
Yes. That's our assumption. Here comes a new flow. We do the calculation.
Like the whole network changes.
Huh?
The whole placement changes.
That's right. That's right. For each elephant flow. Remember our assumption. Yes.
But the network is physical network, right?
It's physical network.
Yes.
Yeah, you won't
can
change.
only change the your network virtualization, like the network function.
Yes.
Right? The
Yes.
Middlebox, the VM that you can change.
Yes.
Right. So even if you come flow, physical network will not change, but for your virtualization, the functions,
Yeah.
NFV that will change.
It may change. Yes. So before I present the solutions for the scenario with a predetermined path, I would like to introduce some concepts. So we divide the Middlebox set into three categories, right? So we name them long ordered, right? So picture A shows with long order, right? It means that there is low dependency relation between any pair of network functions. You can put them in an arbitrary way, right? You can put M first, M double prime, right, and then M prime, or you can put M prime first, right? Arbitrary way, that's okay. So the second category, we call it totally ordered, right? So you can see that there is a dependency relation between any pair of Middlebox, right? So essentially, it's a chain of network functions. You have to follow exactly the order in the chain, okay? And the third category is the general scenario, partially ordered, right? So in picture C, you can see that, right, M prime must be placed before M double prime. But M, you can place it anywhere, right? You can place it here, or between those two Middleboxes, or after M double prime. Okay. So first, let's look at our solution for the long-ordered set placement. Okay. So we use the least first, greatest last rule, and it's very simple. So we sort all the Middleboxes in increasing order based on traffic changing ratios, and place shrinking Middleboxes whose traffic ratio less than 1 from the head of the flow path in increasing order, and place expanding Middleboxes whose traffic ratio greater than 1 or equal to 1 from the end of the flow path. Right? I have a slide illustrates the algorithm. Okay, so let's say this is a flow. It will require 5 Middleboxes. Right, so the first Middlebox has a traffic changing ratio of 0.6. The second one has a ratio of 0.8, 1.0, 1.1, 1.3, right? So for the numbers less than 1, we call them shrinking Middleboxes, right? Because it will decrease the traffic value. So we place them from the head in a decreasing order, one by one. And for those numbers greater than or equal to 1, we call them expanding Middleboxes, right? Because it will increase the traffic value. So we place them from the end of the path in the decreasing order, right, one by one. So use an analogy to help understand. Let's say you're about to graduate, right, and then you got an offer from Google. So you will relocate to Mountain View, right? But you have lived in Miami for several years, right? You got a lot of stuff. Your bed, your sofa, maybe you have a TV. Of course, you can ship all of them to California, but that will cost you a lot, right? So usually what you do, you throw or give away those unnecessary stuff, right, to shrink the size of your luggage, right? And then you drive to or fly to California. After you settle down in Mountain View, right, you started to buy those stuff. So that's an analogy for this idea. Yes?
I'm still a little bit confused on what you mean by shrinking the middle boxes here and the expanding. So the middle box represents a network function.
Yes.
And the shrinking or expanding is a function of traffic intensity?
Yes, exactly. So like the example that I give, before we transfer the data from our site to Tallahassee, we need to compress. So after the traffic leaves this Y accelerator, its volume will only be 30% of its original value. Okay. Okay, so we have this theorem. Of course, right, you gotta put some theorems in your paper to be published in the top places. Okay, so theorem 1, the long-ordered set placement algorithm achieves the minimum path cost. Right, so we prove that this is the optimum. Right, no one can beat this setup. Okay, so that's for the case of long-ordered set placement. Right, next, we look at the totally ordered set placement. Right, how about those Middleboxes have a very strict order that you have to follow? So we use a dynamic programming solution to solve this problem. Right, everyone should be familiar with the dynamic programming. Right, you can have the solution of this problem, right, based on the solutions to the sub-problems. Right, so in this example, so how do you solve the placement of J Middleboxes, right, on the first I hops? Right, you can solve it using the results from the sub-problems, which I'm going to explain in the next slide. Okay, so the idea is very simple, right? So we know what is the best way to place J Middleboxes or less than J Middleboxes on the first I minus 1 hops. Okay, so now you just need to consider one more hop, right? So there are only J plus 1 ways to divide the Middleboxes between the two portions. Right? You either put 0 Middlebox in the first I minus 1 hops, right? Put all the Middleboxes from 1 to J on the last hop, or you put only one Middlebox, right, in the first I minus 1 hops, and put the Middlebox from 2 to J on the last hop. Right? So there are only so many options. The last option is you put all the J Middlebox on the first I minus 1 hops and put no Middlebox on the last hop. Right? So you just enumerate all those possibilities and compare them, select the one with the minimum cost. Okay. So that's for totally ordered set. Right. Finally, let's look at the general scenario, partially ordered set placement. Okay. Unfortunately, it is very hard. Right. So we have the theorem, the Topian problem with a predetermined path for a partially ordered Middlebox set is NP-hard. Right. That's it. The proof is by reduction from the click problem. Right. Click problem finds the maximum sub-completed graph, right, in a given graph. So it is NP hard means that there is no polynomial time optimal solution, right? So what we did is we proposed some efficient heuristic with low time complexity, right? So inspired by the arrow FG arrow, right, which is the least first greatest last rule, the heuristic converts a partially ordered middlebox set into a totally ordered one, so that shrinking middleboxes are before expanding ones in the resulting total order chain. Right. So I want to give you an example about right, the heuristic here. Okay. So I give an example here. Here let's say we have two total order chain, right? So one middlebox with a ratio 1.4 has to be placed before 1.5. Okay. And the other one is 1.6 have to be placed before 0.1. Okay. Of course, those two are the ones you can consider first, right? Because they do not depend on any other level functions. So the naive approach is that we compare them. Right, 1.4 is the less one, right? So we put him as the first middlebox on the path, and then remove it, right? Remove it, and then right. So 1.5 now does not depend on anything, right? We compare 1.5 with 1.6, right? So 1.4, 1.5, 1.6, and finally 0.1. Right. So that's one way to do it. You only look at the first, right, middlebox without dependency. So the other way to do it, right? So we can do some lookup, right? So you can do some lookahead, right? For example, 1.4, 1.5. You can look at both the group, right? If you apply the first two together, right, it will have a combined ratio of 2.1. Right? If you put those two together, it will have a combined ratio of 0.16. Right? Of course, this one is smaller. So we will pick, right? So in the second example, we'll pick the first middlebox in the second group, 1.6. Right? So then we remove 1.6. Right? Do the same thing. Compare this group with 0.1. 0.1 is still smaller, right? 0.1 and then 1.4, 1.5. Okay? Just add some lookup to search deeper into the solution space. Okay? So after we have converted the partially ordered set to a totally ordered set, right? We can apply this TOSP. The algorithms that we used for the totally ordered set placement. Okay, so those are the cases with predetermined path. Right, that's only half of the problem. The other half of the problem is to find the routing path. Right? How about if there is no predetermined path in an arbitrary example? Okay, so general tapping determine both route and place, and it is also NP hard, right? Without a predetermined flow path. The tapping problem is NP hard even for a long order, the middlebox set, right? Even for the easiest case, it's still NP hard, right? And the proof is by reduction from the Hamiltonian cycle problem. Okay, I'm gonna skip the detail. Okay, so our solution is again, right? Since it's NP hard, there is low polynomial time optimal solution. So we propose efficient heuristic. Okay, so what we did is we applied traffic and the space-aware routing heuristic to calculate a flow path with sufficient middlebox spaces and minimize path cost. The idea is very simple. It's just a greedy approach, right? You periodically grab NFV space, right? You look at the servers around you who has a space to host the next virtual machine. Grab it, right? And from there, if you have already got all the spaces, right, you go to the direct destination. Otherwise, just grab another server, right, from your labels. So after you have the path, Right, so we have determined the path, and then you can just apply the NOSP, TOSP, POSP algorithm that we talked about earlier to determine the placement of those NFV Middleboxes. Okay, so next I'm gonna just very briefly explain our SDN-based implementation. Right, so we used this open source SDN controller, Floodlight. Right, it's an open source Java-based module-based SDN controller. Right, and then we use the mininet to create a test bed. Right, so mininet creates servers and the switches as virtual machines. Right, so it's easier for you to do the prototyping. So we the proposed algorithms are implemented as a new module in Floodlight, right? And then we implement some link load monitoring module, right, to monitor what is the current load of different links, right? So we can know which path will be the most appropriate. And also we developed a Middlebox emulator that can emulate the functions of Middlebox. Can drop traffic or increase traffic based on predefined parameter. Okay, so next I'm going to very quickly present the evaluation results. Okay, so since the setup of our started problem has no existing solutions in the literature, right? I mean, the existing solutions, they didn't consider either the traffic changing effects or the dependency relations between them. So we designed some of those benchmark algorithms ourselves. Right? So the first one is first fit. Right? It's very simple. You just place the Middleboxes from the head of your path. Right? One in the case that the path of the flow is determined. The second one is last fit. Right? On the other hand, to place the sorted Middleboxes from the end of the path. The third one is random fit. Right? You place them in a random way. Okay. So when there is no predetermined path, right, we'll just use ECMP, right, which is the load balanced version of shortest path routing, right, to compare it with our traffic and the load aware heuristic. So we have done simulations using NF3 and prototype experiments using the SDN prototype. Okay, so here let's look at the results, simulation results for NOSP. Right, so this figure, right, the bottom figure, the blue figure is for NOSP, and those figures are for first fit, last fit, random fit. Right, we can see that NOSP achieves the shortest delay and the lowest packet loss. Right, so here is the delay and it is a packet loss ratio because of its optimality to place those NFV Middleboxes. So this is to evaluate the TOSP, right, for the totally ordered Middlebox set. So again, the blue curve is our algorithm, and the other curves are the benchmark algorithms. Right, again, TOSP still outperforms other algorithms, but with less margin, right, with less advantage margin, due to the fixed total order between Middleboxes, right? Because the order between Middleboxes have been determined. You cannot switch them. So finally, POSP, right? Remember, for the partial order general case, right, we convert them to total order with different lookup parameter. So we compare the lookup parameter 1 and 2, right? So here, a deeper search into solution space results in better performance at the cost of higher computation overhead, right? So you can see that the red curve, right, is slightly better than the blue curve, which is for the Lookahead parameter of 1 and 2, respectively.
Okay.
Yes?
Well, why is there an elbow at 3, roughly, or between 3 and 4?
Okay, so that's where the congestion happens, right? Before you congest your link, right, all the packets can flow smoothly.
Okay, so that's kind of capacity.
That's right. That's the capacity is reached. Okay. Right. So finally, we compared the TARSA, right? Is the traffic and space-aware routing heuristic, right? So we compared it with ECMP, right? Load balanced shortest path routing. So we can see that TARSA beats shortest path routing due to its traffic awareness in path calculation. Finally, we also have some results from our experiment. Right? So this is experiment to compare TARSA with TOSP and shortest path with TOSP. So as can be seen, experimental data are consistent with simulation data. TARSA achieves a shorter delay and a lower packet loss ratio. Okay, so with that, I'm going to conclude this talk. So NFV is a promising technology to implement network functions, but there are challenges to address. Right? First one is a location problem, service location. Location to place a Middlebox on one of the available servers. Right? There are multiple choices for you. Which one do you pick? The second one is Middlebox traffic changing effects. Right? They may change the value, so you have to be careful when you select the location to place it. Third one is dependency relations between Middleboxes. Right? So in order to deploy NFV with the best efficiency, you have to consider all those challenges. So we have formulated the optimal Middlebox deployment problem as a graph optimization problem and showed its hardness via MP-hard proof. Okay? And then we have designed the optimal algorithms, NOSP, TOSP, to solve some of the special cases, and the efficient heuristic, POSP, TARSA, to solve the general cases. We have implemented the proposed design and demonstrated its effectiveness with simulation and experiment data. Okay, so that's the end of my talk.
Let's thank the speaker. Any questions?
Can any of these things can be used for data centers? I mean, any of the technology or the ideas that you have
Yes.
can be generalized to data centers.
So actually, there is I personally believe it's a trend that the software-based implementation will eventually take over hardware-based implementation. So like for those telecommunication carrier, they are upgrading from 4G to 5G. So based on the old technology, they need to buy many of those new hardware boxes. But now they can keep their servers, just update the functions of the software. So they can put there in data centers, just upgrade the software. Yes?
So I have a question about your heuristic. I guess you had a couple of heuristics, but do you have any theoretical results on how well the heuristics perform? How close to optimal they come?
No, that's unfortunately, we tried very hard to try to derive a theoretical bound, approximation bound, but unfortunately, we haven't.
So you just have experimental.
That's right. So we kind of focused on a different perspective. So we focused on designing the algorithm with no time complexity. So it's realistic.
Sure.
Yeah.
Any other question?
In your, what was it, the experiment phase,
Yes.
you used SDN.
Yes.
How did you use SDN again?
So we used the SDN to first to get the picture of the network, to say what's the load of each link. And then we use SDN to route the flows. So we install those rules on the different switches. So the flow will take the path as we calculated in the algorithm.
I see, okay.
Okay.
And then the environment was actually created with Mininet.
Mininet, exactly. It's easier, faster.
Any other question?
I have a quick question.
Sure.
Follow on that. So I see like the problem that you're solving, it has application in any general network with NFV capabilities, not necessarily for only SDN. So I mean, I didn't see that at least in your talk. Like, is there any connection that is the problem is specific to SDN, or it's just for any general case?
It's for any general case. So SDN is, I would say, a platform that enable us to design a centralized solution that it's easier to implement and will get a better performance because it's a global optimizer. But of course, so you can change the problem context to put the same problem in a distributed network. Then you can come up with a set of similar but slightly different algorithms. And that is a direction that we try to explore.
Okay, let's thank the speaker again.
Good talk. But I want to talk about a little more on heuristics later.
Okay.
Like, I see the reason why set up this context SDN
Because
it's the problem is NFV and SDN not necessarily.
Yeah, I mean,
like
plus
they're
there's always so much
That's right,
about
that's right.
You can have without SDN, you can have NFV.
That's right.
Like, and your problem is actually generally.
Yes, exactly. So the reasoning is that nowadays, you know, that for those top conferences, usually you have to have some
SDN stuff.
no, not you have some system aspect. You have to have some